right, so we just finished going over the warm-up, and I apologize those of you watching the screencast. I forgot to turn screencast on for the warm-up. We did AP problem from 2007, Form B. We did number 3. It's all about wind velocity. It's super fun. Have fun trying it on your own. Feel free to look up the scoring guidelines and talk to me if you have questions. All right, so we're moving on. This is the last section of Chapter 3. So Chapter 3, a huge chapter. We have covered a lot of material. Today is our last section. It has 2 topics in it. So we're going to learn 2 topics. So I only show in here tangent line approximation, but we're also going to do differentials today. So those last 2 topics, neither of them is super long, but I tend to make things long because I like to discuss stuff a lot. So anyway, all right. So section 310, last section. Tomorrow, just so you know, first review day, we're going to finish that quiz 3-2 that we started like a week ago. So we're going to finish that quiz. We're going to do a Kahoot. And then we're going to start working on a review assignment in WebAssign to start getting you ready for your test. Thursday, what happens on Thursday?
Big quiz.
Big quiz. Thursday is the big quiz, right? And then the following Monday, we're going to walk through the big quiz. We're going to do that for maybe walk through the big quiz for maybe a half hour, 40 minutes, take any last minute questions, and then the clock starts. And Monday, you're going to do the essential learning part of the test, which is actually pretty short. And then Tuesday is when you take the rest of the test so that you have a full 70 minutes. Yes, Gavin?
When are we going over the quiz?
Monday.
So before the test?
Correct. Thursday's the big quiz. You don't have school on Friday.
What are we doing on Wednesday?
Tomorrow?
No, next Wednesday.
Oh, next Wednesday, we had skipped section 3-8. And so next Wednesday, which I know is PSAT day, so we're going to do section 3-8. There's no calculus in it. It's really just kind of a pre-calculus review on exponential growth and decay. It's not on your test. But we're just going to cover it just so that we cover it, right? So we're going to do this section 3-8. What I'm hoping to do is do a short abbreviated lesson and then have you guys work the homework in class. If you are out for PSAT, then you just do it on your own. But I'll screencast it if you want to watch it. So, all right, let's move in. Here we go. So linear approximations. Linear approximation, don't write all this down. I'm going to talk a minute. Linear approximation is a fancy way of saying use the tangent line to approximate values on a function. Now, why would we want to use a tangent line to approximate values on a function? Well, number one, a tangent line is easier to plug x's into because it's just a line, right? And when you have to plug x into a linear equation, it's just easier than having to plug it into, a cubic or an exponential or a log or whatever, right? So linear approximation means we use a tangent line and we plug our number that we want to find on the function. We plug it into the tangent line instead of the function. I'm going to show you something for a second. So I'm going to have a seat here. And so every MacBook comes with what is my favorite graphing program, which I don't think most students don't even know exists, but it's there. It's called Grapher. So I love Grapher. It's by far my favorite. And I love it because it works so well in Calc 3. So pick a function that you think is really curvy. Name a function. X to the ninth? Okay. Can we just go with x to the ninth? We don't have to make it super complicated. Okay. So, all right. So we've got y equals x to the ninth, right? So where is this the most curvy? Probably right around here or here, right? Okay. So let's just pretend that we've got this spot right around x equals 3/4 that we're interested in. And it looks nice and curvy, right? Okay, I'm going to zoom in. So still looking at this spot right here. I'm going to zoom in a little more. And I'm going to shift this over a little bit. Okay, I'm going to keep zooming in. Still nice and curvy, right? It's a pretty curvy function. Zoom in a little more. Zoom in a little more. What's going on the more that I zoom in? Whoop. We end up with a line, right? Did I change? Am I not on the function anymore? No, I'm still on the function, right? But the thing is, we call this the linearization of a function. And what that means is if you have any function, no matter how curvy the function is, if you zoom in on a little spot, it looks like a line. Does that make sense? Okay, so any function, if you zoom in enough, looks like a line. Why do we care? Because if we pick a point of tangency and create a tangent line for this function, pretend that's better, the values on the tangent line are almost exactly the same as the values on the function, right? They're super, super close. So why that is kind of the justification of why we can do tangent line approximation. Now, the problem comes with this. So, okay. So if I draw a line tangent right here, like where we've been doing it, somewhere around there, right? Okay. So say it's like right around 0.8 or so. So if I use my tangent line to approximate a value at like 0.81 or 0.82 or 0.79, it's going to work great. But if I use my tangent line to approximate the value at like 1.25, is my tangent line value going to be a good approximation for the y value on the function?
No.
No. So tangent line approximation only really works well for values that are really close to that point of tangency. Once you get far away from the point of tangency, it's just silly. There's no reason to use the tangent line because it's so different from the function. But right around the point of tangency, tangent line approximation works great. All right, so don't save. Okay, so that big long explanation is just talking about what's on the screen, which is saying instead of using the function to compute function values, we're going to use the line to compute function values at values of x near the point of tangency. Now, just so you know, there are like 85 ways to word these problems. So some people call the tangent line the linearization of f. Why is it called the linearization? Because it's like taking your function and turning it into a line, right? So if you see the word linearization, which your book really likes, that just means tangent line. If you see tangent line approximation, that means tangent line. If you see linear approximation, that means tangent line. If you see local linear approximation, that means tangent line. No matter how they word it, it all means the same thing. It just means find the tangent line and then plug into the tangent line. That's all it is. It's just a bunch of fancy words for the same thing, which is find the tangent line and plug into there. All right. Now, this problem, this is from your book. Okay. And your book tends to ask these problems a little bit different from how the College Board words them. So we're going to do one based on how your book asks the problem, just so you got to get the feel for it. And then the next problem I'm going to give you is an AP problem. So we'll do some regular book practice, and then we're going to do some AP practice with the same concepts so you can see. So find the linearization of the function f of x equals square root of x plus 3 at x equals 1. What do they mean by linearization? They mean tangent line, right? That's all they mean. You're just finding the tangent line. So when we find a tangent line, what two things do you need? Point and slope, right? Where do we get the point from? Plug it into where? Original function. Where do we get the slope from? The derivative, right? So I want you all to take a minute or two in your groups, and I want you to find the line tangent to this function at x equals 1. And then just kind of pause there. Okay, so first let's find the point. Lining it up. Okay. So to find the point, so we need f of 1 which is square root of 4. Is that plus or minus 2 or just 2?
Just
Are you sure?
just
Yeah. Yes. Because a function. If it's not a function, it has two values.
That is true. There's a lot of reasons that it's just 2. It's just 2. This is so I've had this come up. It came up in Calc 3 yesterday. We had to have this discussion again. So there is a big difference between this. Oops. Yeah, and x equals and this, right? This is a quadratic equation. So when you're solving a quadratic equation, a shortcut method is to write x equals plus or minus the square root of 4, which is plus or minus 2, right? But technically what you're really doing, exactly, you're factoring, right? Which is how, so it's 2, right? But we learned long ago when there's no middle term that we can just take the square root of both sides as long as we put a plus or minus to accommodate both solutions, right? This is just a shortcut method for doing this. Once students learned this, students started thinking plus or minus had to go in front of every root in the world. Have you ever learned something new and then felt like it had to apply to everything you've ever learned, right? And it doesn't. It's just in this context, right? The square root of 4 is just 2. Right? If there's no plus or minus in front of it, you don't get to add your own in, right? So it's just 2. So be careful that you know that a square root function just has, all the outputs are going to be positive or 0. Okay, so there's our point. So our point is 1, 2. Now we need the slope. What do we use to find the slope? Derivative, right? So our f prime, so 1/2 times x plus 3 to the negative 1/2. There's a lot of talk of chain rules. Everything in the world is chain rule, right? Every single derivative you do is chain rule. It's just that the derivative of the input on this one just happens to be 1. So you lucked out if you didn't know chain rule because it ended up not making a difference. So you end up with 1/2 root x plus 3. Every year, I have students do the same thing. So I'm going to write what not to do. So please don't do this. So I know it's bad to tell students what not to do, but there's at least 2 people in the room who are going to do this. So I'm hoping this like squishes that. All right. Y minus 2 equals 1/2 root x plus 3 times x minus 1. There's my tangent line. Right? Right? It's perfect. Point, slope, done. Right? Okay. Except, is this a line? No. The whole definition of a line is that the slope has to be a constant, right? Never put your derivative function in for the slope. You have to actually find the slope at x equals 1. You need to plug the 1 in. So please, please, please do not put in a function. And you should be thinking, like in your head, I want to know that there's thought going on beyond just memorizing and following steps. I want to know that you actually read the problem and it said equation of a line and that you looked at your answer and thought, is this a line, right? So you should ask yourself, is this a line? If it's not, you've done something wrong. So we got to plug in the 1. So f prime of 1 is 1/2 root 4, or 1/4, and there's our equation. When you're doing linear approximation, it's usually honestly easier if you go ahead and solve it for y. You don't have to, but I'm going to just move the 2 over. I'm not going to do anything major. I'm just going to put the plus 2 on the other side because I have to plug a bunch of numbers in for x, so it's easier if it's already solved for y. All right, so any questions on tangent line? That's all old review, right? Okay, so what makes this new is we're going to use the tangent line to approximate function values. Now here's where the book and the College Board differ. The book is saying use it to approximate the square root of 3.98, whereas the College Board will say use it to approximate f of 0.98. So what's the difference? Is the book doesn't tell you the x value. They're giving you, hey, what's the square root of 3.98? You need to find the x value to plug in. So it's whatever number is being added to 3, right? So the College Board will say, hey, so this would be like an x value of 0.98 because it's 0.98 plus 3. But to clarify, I'm telling you that that's f of 0.98. So it's really saying, let's approximate the function value at x equals 0.98. So when you do tangent line approximation, you're just plugging the 0.98 into your tangent line instead of into your function. So we get 1/4 times 0.98 minus 1 plus 2. Now, if this was the AP exam, could I leave it like this?
Yes.
Yes, absolutely. Something tells me that if this was a test, we would make you simplify. 2 plus 2. So let's see, we get negative 0.02 over 4 plus 8 over 4. So I get 7.98 over 4. I do not like decimals within fractions, so I would probably make you clean this up by multiplying top and bottom by 100, and then you get 798 over 400. And then you could reduce that if you want.
Will it say to do this though on the test? Did it simplify it?
I don't know. I honestly, it's not a yes. I'm telling you the truth. I don't know. I just don't remember, honestly. So it's been a while. I've actually been working on your chapter 4 test for the last week, so I've completely forgotten the chapter 3 test. So I gotta get my head back in. Okay, so I want you guys now to do the same thing for the approximation of the square root of 5.05, which is the same thing as f of 2.05. So I want you guys to use your tangent line to approximate f of 2.05. So take a moment, plug a 2.05 into your tangent line, and see what you get. Did you stop? Why? Unless I say simplify. Yes, you may. See, it's not okay. Okay. I'm going to work while you guys are still simplifying. Did you get something similar?
Yeah.
So higher, I can't tell. Yeah? Okay. All right. How about in the back? Charles, how you doing? Yeah? Okay. All right. Now, we're not done. There's a third part of the question. The third part of the question says, determine if these values are overestimates or underestimates of the actual values. Now, next unit, chapter 4, I'm going to teach you a mathematical, analytical way where you won't need a graph to determine if these are over or under estimates, but you can't do that yet. It involves the second derivative and a little stuff, but anyway. So for now, what I ask you to do is sketch a graph and look at it. So we're going to sketch the graph of root x plus 3. Now, the square root of x plus 3, that's the same as the graph of root x shifted how?
Or 3 on.
The square root of 3.
3 to the left.
Which one is it?
3 to the left.
Are you sure?
Yes.
Yeah.
Square root. Because it's x minus 3 to the left.
Do you all agree?
Yeah.
Yeah.
All right, it's 3 to the left. Okay, so we go 3 to the left. We draw a square root function, looks something like that, right? We're at x equals 1, but in all honesty, no matter where we are, the answer to this question is going to be the same. But if you sketch a little tangent line at x equals 1, look at the values on your tangent line versus the values on your function. Are the values on the tangent line going to be higher or lower?
Higher.
They're going to be higher. So therefore, these would be overestimates. Overestimates. Because all your values are above the function. And I'm going to give you a tiny preview. Anytime your function is shaped like that, or any part of this is called concave down, the tangent line is going to be an overestimate. No matter where you are, it's going to be above the function. Anytime your function is shaped like this, concave up, your tangent line is going to be below the function, and you'll have an underestimate. So I like to say, down like a frown, up like a cup. So yes, Alex.
What are the benefits of doing this estimation if you're actually looking at
It allows you to evaluate, like, very quickly you could find a ton of function values if you didn't have a calculator without having to do a terrible amount of calculations, right? So if I needed to know, like, I wouldn't off the top of my head know the square root of 2.05, but I know I could plug it into the tangent line without too much trouble. Yes?
Is the test full, like, all in one?
Yes, the entire test is no calculator. Good question. All right. Good. That's like part 1. We got a lot to do. All right, so moving on. So, AP problem. And I love it because it gives you like a function we haven't done in a day or two. So, grass clippings. This is from 2014, number 1. Grass clippings are placed in a bin where they decompose. For time values from 0 to 30, the amount of grass clippings remaining in the bin is modeled by A of t equals 6.687 times 0.931 to the t. What kind of a function is that? That's exponential. The variable's in the exponent, right? Okay. Where A of t is measured in pounds and t is measured in days. For t values greater than 30, L of t, the linear approximation to A at t equals 30, what's another word for linear approximation? Tangent line, is a better model for the amount of grass clippings remaining in the bin. Use L of t to predict the time at which there will be a ½ pound of grass clippings remaining in the bin. Show the work that leads to your answer. So here's what I want you to do. So number 1, I want you to find L of t, which is the equation of your tangent line, right? Before you do that, I'm going to give you a little refresher because people tend to forget. So if y equals a, I'm going to put to the u because for some reason I still have a bunch of students who have like an honest mental block against chain rule. So if you just memorize all your derivatives with chain rule built in, then I think maybe it'll help you remember chain rule. So anyway, so if y is instead of a to the x, I'm going to do a to the u, where u represents any function of x. So if y equals a to the u, then y prime is a to the u times u prime times ln a. Right? So just in case you've forgotten your formula for the derivative of a to the x, that's how you do it. Okay, so I want you to find the equation of the tangent line, then reread the problem and make sure you answer what it's asking for, because there's a tiny twist to it. So take maybe 2 minutes or so. You can work it on paper, but talk to your group members too. Make sure you're working together. You someday I will learn. Okay. It is so important that you understand the difference between y equals x squared and y equals 2 to the x, right? This one, I can do power rule. Put the power in front, reduce by 1. This one, I can't. Because this one, my power is a number. This one, my power is an exponent. I can't do power rule. I have to do exponential rule. So this is when the variable's in the exponent, you can't do power rule. You have to do exponential rule. There's no way around it. So our derivative, a prime, what is 6.687? That's just a coefficient. It just comes along for the ride, right? So 6.687 gets multiplied by your answer. This is like a to the u. So your a is 0.931, your u is t. So if I have a to the u, the derivative of a to the u is a to the u times the derivative of t. What's the derivative of t? 1 times natural log of a. That's your a prime. What two things do you need for the equation of the tangent line? Point and slope. So is this the slope, or do I have to do something still? I have to plug in a, okay, what x am I going to use? 30. I have to plug in a 30 because they said at t equals 30, right? So you need your slope at 30, and then you need your point at 30. So I'm going to start revealing the answer so you can see it. All right, so a prime of 30 is around negative 0.055976, something around there. Just so you know, your final answer has to be correct to 3 decimal places, so never, ever, ever round in the middle of the problem, right? Always carry all the decimals through to the end. So that's my slope. To find my point, I use the original function. A of 30 is around 0.7829-ish. All right. And then I write my equation. Now, they don't write the equation. They give you this funky thing. I'm going to go ahead and write it out. So first, you know what? I'm going to write it first with y and t, and then I'm going to call it all t. So y minus 0.783-ish equals negative 0.055976 times t minus 30. All right. So to solve for y and give it the name that they want, which is L of t is around negative 0.055976 times t minus 30 plus 0.782928. All right. All of that, that's L of t. So that was worth 2 points, just so in case you're wondering. That was worth 2 points. Any questions before we move on finding the derivative or writing the tangent line? Okay. So let's read this. Use L of t to predict the time when there will be 0.5 pounds of grass clippings in the bin. So where does that 0.5 get plugged in? Is that a t value? That's an L of t value. They're kind of doing it backwards. They're giving you the L of t and they want you to solve for t. So you plug in a 0.5 for your L of t, and when you solve for t on your calculator, you get around 35.05. And this would be days. So, a little word of comfort in that there are no decimals on your test because it's a no calculator test. But the fact that there are decimals shouldn't throw you too much. The way you do the derivatives doesn't change just because a number has a decimal in it, right? It's still the same kind of derivative. Okay, let's move on. But you know what? I'm just going to say one more time for the video. Recapping. All right? I know this felt hard, and mostly it's just because we've got to get comfortable with all these different kinds of derivatives, right? But in general, the main point, find the equation of the tangent line, plug in the number. That's really all it is to linear approximation. Is find the equation of the tangent line, plug in the number. It's just that those tangent line equations, you got to know all those different derivatives to find the slopes. This is it. Last topic of the unit. So no more learning to do for over a week. Your brains can relax and just review and get ready, right? Okay. So this is a small step into a world of differentials. Differentials are not on the AP exam, but they're a fairly big topic in Calc 3, and it's kind of good to have at least a tiny little bit of exposure to them this year, just to help you get ready for the big stuff that you have to do next year with them. And it also helps you a little bit with understanding how derivatives work. So today is going to be our first step into differentials. And I'm going to show you, I have this beautiful picture. See how nice and simple it is, right? Yes. Okay, I have this beautiful picture so you can see visually what a differential gives you. So first I'm going to show you the graph, and then I'm going to talk to you about it with an application. So if we have this curve, see the blue curve right there? So we have an x, and then we have another x value. The difference between these two x values is called delta x. Okay, so this is x plus delta x, right? And so they've actually shown it right here. So this is our delta x. Now, on the graph, like on the actual curve, the difference between the two y values is delta y. If we were to do the slope between this point and this point, it would be delta y over delta x, right? Change in y, change in x. It's your old-fashioned slope between 2 points. All right? Are you with me? Yes. Okay. So this, just so you know, this is the y value associated with this x value on your function. We, in life, have found that it's easier to approximate delta y than to actually calculate delta y. So how do we approximate delta y? If we draw a line tangent to the curve at this point, and then plug in our x plus delta x into the tangent line, now the difference between the two y values, which is the difference on the tangent line, is called dy. So our delta x is called dx, but now we have a new change in y because it's the change in the y values on the tangent line, not the change in the y values on the actual function. And what you'll find is, as functions get more and more complicated, dy is actually much easier to find than delta y. And when you have large numbers of computations, dy is more often what is used to find them. So, and here's where I'm the most common. So the book talks about maximum allowable error in product production. So here's what we mean by that. So suppose you are manufacturing canned peas, okay? All right. I couldn't think of something in a can, so I don't know why peas came to mind. So you're producing the cans and then filling them with peas. So what happens is when you produce the can, right? You have this metal can that you're manufacturing. Say that you are claiming that the radius, say it's like, I don't know, like this size can, right? So say you're saying it has like a 1-inch radius, right? Okay. So our metal cans have a 1-inch radius, except they're produced by machines. It's not like they're perfect, right? Nothing is perfect. So no radius of any can is going to be exactly 1 inch. They're going to be close, but they're not going to be exact. So companies they actually have to report they're allowed a certain amount of error in their production. And that error is called the maximum production error or whatever, right? So say like the radius of your can has to be correct within 0.01 inches from what it really is, right? Or something like that, right? So whatever your maximum allowable error is in your production. So the radius of our cans is actually going to vary, between like say 0.9 and 1.1. Well then how does the change in the amount of peas vary? By volume. How is that affected by the error in the can, right? Okay. I am so sorry we ran out of time. I will finish this. Wow, here. Okay. So that being said, let's go ahead and work a problem. So here's what we have. If y is this beautiful x cubed plus x squared minus 2x plus 1 function, and we have to think about that representing something, whatever it happens to represent. It might be the production of some container, it might be whatever. So we're going to compare the values of delta y and dy. So if we're going to do delta y first if x changes from 2 to 2.05. Delta y is simply the change in y. So it's f of 2.05 minus f of 2. So again, it's another decimal thing, so you're welcome to use your calculator to calculate this. So I get that f of 2.05 is around 9 point, I need my glasses. Okay, 9.717625. And then f of 2 is 9. So my delta y is around 0.717625. All right, and that's approximate. All right, so that's our change in y on the actual function. Now to find dy, what we're going to do is use the derivative. So we're going to find dy dx, just like we normally do. So our normal derivative, 3x squared plus 2x minus 2. But we don't want dy dx, we want dy. So we're actually going to multiply both sides by dx. Oops. Plus 2x minus 2 times dx. We're going to multiply both sides by dx. And remember, our dx is the same as our delta x. So our dx, which is our change in x, 2.05 minus 2, or 0.05. All right, so we want, okay, they said for this problem to find dy at x equals 2. So dy at x equals 2 would be, well, it's this function evaluated at 2, which if you plug in a 2, you get 14 times dx, which is 0.05. And when you do that, you get 0.7. So your actual change in y was around 0.717. Your approximate change in y is around 0.7. They're pretty close. And so that's why we can use our dy to approximate changes in our output values on our function. And that's it. So that was the only part that we didn't get to within class time today. I'm so sorry about that, but hopefully it wasn't too hard to pull it up and watch it. And I'll see you later.